Turns out that in the study of calculus, being able to find points of horizontal tangency ends up having a big significance and a solid meaning. I'm not going to go into a lot of what that means now. The short of it is it really helps us to find maximum and minimum values. So if you want to find the highest or the lowest point in a function, finding the horizontal tangents is really helpful. So that's sort of our motivation for this lesson, but in this lesson I'm just going to be focusing on the mechanics of how we go about finding a horizontal tangent. Before I go any further on that though, think about what a horizontal tangent would mean, right? What it means is that you've got a point in a function where, well, where your tangent is horizontal. And what does that mean? Like we should be able to do something with that numerically, right? If you have a point where there is a horizontal tangent, it basically means that the derivative at that point will be 0. Right? So when we're looking for horizontal tangents, we're effectively going to take the derivative and set that equal to 0. Now, it's also worth mentioning that so when we set the derivative equal to 0 and solve for x, all that finds for us is the x value. So if I had axes here, doing that is only going to find me what this x value is. If I want to know the point of horizontal tangency, I'll need not only this x value, but also f of x. I'll need to plug that back into the original function to find the y-coordinate of the point of horizontal tangency. So my first example here, find any points at which the function g of x equals x cubed minus 6x squared plus 9x plus 4 has a horizontal tangent. So we mentioned previously that if you want to find horizontal tangents, we take the derivative and we set it equal to 0. So we begin by finding the derivative of this function. This should be something that all of us can very easily do. So pause the video and find that derivative. Each one of these terms that's connected by addition and subtraction, we can just use the power rule on. So the first one is 3x squared, the next one is 12x, and the last one is just 9. The derivative of 4, because it's a constant, becomes 0. Now that I have that derivative, we set it equal to 0. So 0 equals 3x squared minus 12x plus 9. This is a quadratic, which means we can solve it by factoring. 3 times x squared minus 4x plus 3. And whatever method you use for factoring, we can do that. This is going to end up being x minus 3 and x minus 1. So then when I set each of these components equal to 0, we get 0 equals 3, which is clearly incorrect. 0 equals x minus 3, and 0 equals x minus 1. When I solve these two, I find that my points of horizontal tangency will happen at negative 3 and at positive 3 and at 1, but those are not the points of horizontal tangency. This question asks us to find the points, and so the only way that we can do that is by taking these values and plugging them back into the original function, right? Evaluating the original function for those values. So we can figure out what is g of 3. If I were to plug in 3 up there, I'd get 27 minus 54 plus 27 plus 4. Right, and so if I sort of move this up a little bit, it looks to me like g of 3 is going to be 4. And I can do the same thing with 1. If I do g of 1, I'll end up with 1 minus 6 plus 9 plus 4. So let's hear what is g of 1. Let's see here. This is 13, 14, minus 6 is 8. Okay, so now we can see that our points of horizontal tangency are at 3, 4, and 1, 8. So these are the points of horizontal tangency. Okay, so wonderful. We found the x values where the slope was 0. We plugged those numbers into the original function, and those gave us the y values. These 2 points are my points of horizontal tangency. I have one more example for us, which covers, one, all of the ideas about horizontal tangent that we just picked up, but 2, also gives us a chance to practice one of those trigonometric derivatives that we learned in one of the previous videos. So I'd really like you guys to do as much of this problem as you can on your own. So pause the video, try it on your own, and check back in as necessary. So to find the points of horizontal tangency, we first need to set the derivative equal to 0. But I suppose before that we even have to find the derivative. So what is h prime of x? The derivative of this will be negative 4 sine x plus Great. So now that's the derivative. I now set this equal to 0 so that I can find the points of horizontal tangency. So I have 0 equals negative 4 sine x plus 2. Right? Our strategy on solving any problem like this is always to basically isolate the variable portion, so isolate the sine x, and then solve from there. So, I can move the 2 over. From there I can divide by negative 4 and get 1/2 equals sine x. Right? And then from here, I need to find solutions for this on this interval. Right? So I'm effectively now saying that x is the inverse sine of 1/2. Right? And this is where we need to now sort of think, like, where is the sine 1/2? And this should remind you back of your unit circle days, right? Where will we find a y value of 1/2? Well, that happens over here. It happens over here where x is pi over 6. But I'm looking for any points on the interval from 0 to 2 pi. So anywhere around the unit circle from 0 to 2 pi, do I anywhere else see a sine value of 1/2? Well, sure we do. We see one over here in the second quadrant. This value over here. X could also be 5 pi over 6. So now that I have these two values, these are the locations of the horizontal tangents, but if I want the points of horizontal tangency, I need to evaluate my function at these two x values. So I'll move on and do that next. To do this evaluation, I need to do h of pi over 6. So I'll have 4 cosine pi over 6, plus 2 times pi over 6. And my other one here, I also need to do h of 5 pi over 6. This will be 4 cosine 5 pi over 6 plus 2 times 5 pi over 6. Alright, so if I just sort of go through and evaluate these things, h of pi over 6, we've got 4 times the cosine of pi over 6, that'll be root 3 over 2, plus, and this just simplifies to pi over 3. If I continue working with this, h of pi over 6 is 2 root 3 plus pi over 3. And so now that I have that, I can actually write the point. The point of horizontal tangency is pi over 6, comma 2 root 3 plus pi over 3. And I want to take a brief second here to talk about that point we just found. A lot of people get anxious when they see this y coordinate, because they're like, oh no, that's not a number. There's like a plus in it, there's a pi. This is a strange number, but this is all just one complicated number. So this is really straightforward. This is an x coordinate, this is a y coordinate. Nothing wrong with it. Okay. For the next one, h of 5 pi over 6, we can sort of do this one more quickly. This is going to be negative root 3 over 2, and so when I multiply these two things together, I'm going to get negative 2 root 3. Plus this one over here is going to be 5 pi over 3. Sounds good. That's the y coordinate. I shouldn't have boxed that. That's because that's only the y coordinate. If I want the point, I need to say that it's 5 pi over 6. It's my x coordinate, and then my y coordinate, negative 2 root 3 plus 5 pi over 3. These are my 2 points of horizontal tangency on the interval from 0 to 2 pi.